Hello and welcome to my science tutorials. Today we are back with a brand new video on alkanes and their nomenclature. So at the end of this video you should know almost everything about alkanes, their nomenclature as in how to name them, and then how to draw the structure of an alkane using their names. Okay, so without wasting you guys your time, let's get started. So what are alkanes? Now alkanes are saturated hydrocarbons. So what we mean by saturated hydrocarbons is the fact that alkanes have carbon-carbon single bond. So you see maybe a compound like this with H all around. Okay, so this is a typical example of an alkane. To be precise, this is 1, 2, 3. It's 3 carbons, so this is propane. Okay, so this is an alkane, and then you can see we have carbon-carbon single bond over here. Okay, and because we have just carbon-carbon single bond, these bonds are said to be what? Saturated. Saturated in the sense that in the formation of this single bond, it is an axial overlap, okay, of the orbitals that form this bond. Okay, so this bond is very strong, and then it requires a higher amount of energy to be broken, so they are saturated, and then they are highly unreactive. Okay, so alkanes are saturated hydrocarbons, like I said, and then they have the general formula CnH2n plus 2. Now where n is the what? Is the number of carbons. Is the number of carbons. So let's have, for instance, an alkane with 1 carbon, okay, implies n is equal to 1. So we have what? Let's use the formula over here. So we have C1H2 into bracket 1 plus 2. So it's what? C1, this is H4, okay, so which is technically CH4. So the simplest alkane we can get has the molecular formula CH4. So we write it like this: CH4. Now let's take a look at something. If you've done hybridization and you know your hybridization, then this shape should tell you something. Okay, so this is a tetrahedral shape. Okay, so this is the tetrahedral shape of a molecule. Any molecule having this shape is called tetrahedral, and then it has a bond angle of what? 109.5. 109.5, and then it means the hybridization of the central atom over here is what? sp3 hybridized. Okay, so let's dive a little bit into what we mean by the sp3 hybridization of the carbon atom at the center. Okay, so if we consider carbon has the atomic number 6. Okay, so it means when we are drawing the ground state electronic configuration, we have 1s, then we will have 2s, then we have what? 2p, sorry, so this will be the 2px, this will be 2py, and then 2pz. okay, so carbon is 6, so we have 1, 2, 3, 4, 5, and 6. This is for our ground state electronic configuration. Now in the excited state, okay, in our excited state, we have what? We have the 1s, 2s, and then we have the 2p. So we have 1, 2. During the excited state, one electron is what? Excited, so it moves from here to the 2pz empty orbital over here. So we have just 1 over here, then we fill this also 1, 1, 1. Okay, so if we combine these orbitals, which is the ones we have over here, then we tend to get what? 4 equivalent what? sp3 hybrid orbitals, which means if we combine the everything we have over here, we'll be having 4 orbitals, okay, and they should be the same. So we have this. So this is our 4 equivalent sp3 hybrid orbitals, okay. The fact that there is 3 here doesn't mean it's supposed to be 3 orbitals, okay. So this simply means the sp3 means we have 1 s orbital and then we have 3 p orbitals, okay. Precisely, we have what, a 2s orbital and then 3 of what, 2p orbitals, okay. So this is how from here, okay, it means carbon can form what, 4 bonds. So it can allow for other elements to bring their 1 electrons all together so that they will form a bond. So you can pair this up. So this will be 1 2 3 4. So it means carbon can form what, 4 bonds, okay. So it has room for 4 more electrons, okay. So it can form 4 bonds, and then if you can form 4 bonds, your geometry is what, tetrahedral, and then you have a bond angle of what, 109.8. So this is a little bit about the hybridization of carbon and how come alkanes are what, sp3 hybridized, and then they have the tetrahedral shape. So now that we are a little bit conversant with what alkanes are and then how their structure and then their geometry is, let's have a look at the nomenclature of alkanes. Now, the first thing you want to note when you are naming an alkane is what, is to what, find the longest continuous chain, okay. So you find the longest continuous chain or the parent chain, okay. So you need to find, let's have, for instance, we have this as our alkane, okay. Then we have another carbon here, we have another carbon here, maybe we have another carbon, then another carbon over here, okay. Then we have one and one over here. This is just the skeleton, so we are not adding anything, okay. So if this is our alkane, we need to number the carbons and see which one will give us the longest continuous chain. So we can, from here, we can either count this, okay, as 1, or we can count this as another one, or we can count from here as another one, okay. So let's look at each of them and see which one will be the longest. So if we have 1 2 3 4 5 6 7 8, that is if we are counting this way. Let me use another color. So if we are counting this way, we can have 1 2 3 4 5 6 7. So we have 7. Now let's count in another way. So let's count this way. So we have 1 2 3 4 5 and 6. So from the look of things, it is clear that what, if we count this, if we take this as our longest continuous chain, then that makes sense because we have 8 carbons in this row. If we are counting like this, we have 7. From this side we have what, 6. So we will be taking what, our longest continuous chain to be what, to be 8, okay. So now after we find our longest continuous chain, okay, any other atom attached to the longest continuous chain becomes what, a substituent, okay. So a substituent is any other any other compound or group of atoms, okay, attached to the longest continuous chain of an alkane. So in our example, this is our longest continuous chain, okay. So this carbon here and then these 2 carbons, including these ones, are all what, substituents, okay. So now that we know what substituents are, let's dive a little bit more. So in chemistry, we have 2 groups, or like 2 general classification of substituents. We have the first one, which are the inorganic ones, and then they include the halogens. So we have this bromine, where we call as a substituent, it's called bromo. Chlorine will be called what, chloro. Then iodine will be called iodo. Then we also have NH2, which we call what, amino. This is the amino group. And then we also have what, the NO2, which is what, the nitro group. We also have the CN group, which is the cyano group. So these are all what inorganic substituents. Okay, now the organic substituents that we have, they are what? The alkyl groups. So what are alkyl groups? Well, alkyl groups are just alkanes lacking one hydrogen. What do I mean? Remember I said alkanes have the general formula CnH2n plus 1. Okay, and then the definition of an alkyl group is what? An alkane losing, like, with one hydrogen being lost, and here is 2, sorry, for an alkanes here is 2. So for the alkyl group, their formula, their general formula is what? CnH2n plus 1. Okay, so so we have the alkane. The first alkane we have is CH4, which is called methane. Okay, so the alkyl part of this will be what? CH3. It will lose one hydrogen. Okay, and then because this one is called methane and it's an alkane, the other name is from here, and then the one without the hydrogen or losing one hydrogen is an alkyl group. So this, instead of being called methane, let me write instead of being called methane, okay, the CH3 will be called what? Methyl. Okay, so we only add what? The YL over here to the methyl, to the name meth, the prefix meth, to get the functional group of this. Okay, so we'll be looking at this into much more details when we try to solve, like, name our organic compound. Okay, so after we now locate our substituent, then we need to give them priority. Okay, so let's look at this example. So in this example, we have this as the first substituent, then we have other ones as the substituents as well. So we have this carbon over here as one substituent, this as another substituent, and then these two as another substituent. Okay, so we need to give them numbers in such a way that what? If we add all the numbers, it will give us the least possible. What do I mean by this? This carbon is on carbon 3. Okay, so the carbon over here is on carbon 3 if we are counting this way. Okay, so this is carbon 3, so we have one carbon on carbon 3, so 3 for one carbon. Okay, then the next carbon is what? On carbon 4, so we have 4, another carbon. Then we have 5, another carbon. Okay, so in total this is 9, 10, 11, 12, so we have 12 over here, if in case we count from here to here as our longest continuous chain, and in this direction. So assuming we go in the reverse direction, okay, we will be having this as our carbon 1, carbon 2, carbon 3, carbon 4. So the substituent we have over here will be on carbon 4, so we have 4. This will be on carbon 5. This will be on what? Carbon 6. Okay, so if we add this, we are getting what? 15. So in this example, there's no way you will name the substituents, okay, by counting the carbons from here in this direction, because it will give you a higher locant. Okay, so we name the substituents, we give them numbers that will give us what? The least locant possible. Don't worry, I will be looking at how to do all of this with practical examples so that you can understand. So now that we know how to find our substituents and then how to give them the least locant, the next thing we want to look at is the fact that if we have two of the similar substituents, we use the prefix di for 2, tri for 3, tetra for 4, and all that. So if we have the same substituent, they appear 4 times, so you'll be like something something di something. Okay, so we also do that, and then we name the substituents alphabetically. So if one substituent is methyl and then another substituent is what? Bromo. Okay, so when we are writing the name, B comes first before M, so we should write what? Bromo first before we write what? The methyl. Okay, so with this general explanation of what an alkane is, how to name the alkanes, let's have a look at some few examples so that we can understand what we mean over here. So let me write our topic, alkanes. Okay, so let's have a look at the first example we have over here. So we have CH3Cl. So whenever you have a compound like this, try to write it, expand it so that you can see how the atoms are bonded. So we have C, 1 carbon, then we have 3 hydrogens. Okay, then we have 1 chlorine. Okay, so over here we only have 1 carbon. Okay, now if you have 1 carbon, the prefix is what? Meth. If you have 2, it is what? Eth. 3 is prop. 4 is but. 5 is pent. 6 is hex. 7 is hept. 8 is oct. 9 is non. And then 10 is dec. Okay, so these are the prefixes, and because they are what? Alkanes, we add what? The ending A, N, E to all of them. So an alkane with 1 carbon will be named what? Methane. With 2 carbons will be what? Ethane. 3 carbons, propane. 4 carbons will be what? Butane. The same way, you just add the N to them because they are alkanes. Okay, okay, so once we have this thing down, let's name this compound. Now the parent name of this compound, okay, because it has 1 carbon, so it will be what? Methane. So we write that one down, methane. Now, do we have any other, like, do we have any substituent? Yes, we have. This is a substituent. It's not a carbon, so it does not form part of the parent chain. Okay, hydrogens are not considered substituents, so let's take note of that. So the chlorine over here is a substituent. Okay, so in this example, what we will have to name the substituent before the parent name. So we will have what? Chloromethane. So the name of this compound, okay, is what? Chloromethane. Mind you, you write them together, you don't put a space between them. It's because I named the parent structure first. That is how come we have that space. So for this example, this compound is called what? Chloromethane. Now let's try another example. So example number 2, we have CH, then we have Cl3. So we have 1 carbon, so we write the carbon down. We have a hydrogen here, we write the hydrogen. So we have 3 chlorines, so we had 1 chlorine, 2 chlorine, 3 chlorine. Okay, so still we have 1 carbon as the parent carbon, so the name of this alkane will be what? Methane. So we write the methane down. Now how many chlorines do we have? We have 1, 2 and 3. We have 3 chlorines. So because we have 3 substituents and they are all chlorine, we need to give them a prefix what? Tri. Tri means what? 3. So this is what? Trichloro for the 3 substituents we have over here. Okay, so the name of this compound will be what? Trichloromethane. So this is trichloromethane as the example number 2. I hope we are all on the same page. So let's look at another example. Now let's go into a more complicated example a little bit. So we have CH2Br, then we have CH2Br again, CH2Br. Yes, so over here we have the first carbon, so we write this first carbon. It has 2 hydrogens attached to it. 1, no, these are in brackets, so 2. So the Br in the bracket means it is attached to this carbon. Okay, so linked to the second carbon. Then we have it also has 2 hydrogens. Then we have another bromine. Okay, so in this example we have how many carbons? We have 1, 2. Okay, so our parent name for this compound, our parent name, let me use PN as our parent name, will be what? 1, 2. So it's what? Meet it, so it's ethane. So we write what? Ethane here. That's our parent name. Okay, now do we have any substituents over here? Yes, we have 2 substituents. Okay, now one is on carbon 1, one is on carbon 2. So in this example, it doesn't matter whether you name this as carbon 1 or carbon 2. We will have 1 bromine on carbon 1 and then 1 bromine on carbon 2. So we can count from any side. Okay, so our substituent, okay, we have what? 1 bromo, and then we have what? 2 bromo. But then we don't write them like this, okay, because they are 2 substituents and they are the same substituent. Okay, 2, but then they are the same. Bromo, they are all bromine. So we write what? 1, 2 bromo. Okay, now take note of something. Did you see when I was writing 1 and then the bromine, which is the bromo, I put hyphen over here. When I was writing 2 numbers, I put comma. That is how we name. So in naming organic compounds, we differentiate numbers by a comma, and then a number and then a word by a hyphen. Okay, so now that we know we have 1, 2 bromo, and then our parent name is ethane, we just join these 2 names together to form the name of our compound. So the name of this compound, oh sorry, this is supposed to be what? Dibromo, because we have 2 bromine, so it's dibromo. Sorry about that. So the name of this compound is what? 1, 2 dibromo ethane. That is the name of this compound. So it's what? 1, 2 dibromo ethane. So let's have a look at another example, a more sophisticated and then complicated example. Okay, so let's name this one. We have CH3, CH2, CH into bracket CH3, then we have CH into bracket CH3, and then 2. Okay, so first of all we need to draw the structure. So we have 1 carbon, we have this carbon with 3 hydrogens, so carbon H, H, H. Then bonded to the second carbon, it has 2 hydrogens, so we have 2 here. Then the third one, which is C, it has 1 hydrogen, and then a CH3 attached to it, so we have the CH3 here. Then bonded to this carbon with a hydrogen, we write it over here, and then 2 CH3s, so we have CH3 here, CH3 over here. Now this is a perfect example. So we have 2 ways of like getting the longest continuous chain. So we have, this is, we can name from either this way or this way. We can number those ways. So we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay, this is our longest continuous chain, the first one. Okay, then the second one we can name in the other direction. So we can name this as our carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay, so if this is the naming, okay, the numbering we have over here, so it means our parent name, okay, our parent structure has 5 carbons, so 5 carbons is what? Pent. So our parent name is what? Pentane. So we have that down. Now can we notice the fact that this group and this group, okay, they don't form part of the parent structure. These 2 groups, okay, they don't form part of the parent structure, so they are what? Substituents. Okay, now we can see this is a CH3. Okay, so this is, like I said, it's an alkyl substituent. okay, an alkyl substituent. Because it also has one carbon, it is what? Meth. But then because it's an alkyl group, instead of saying what? Methane, as in alkanes, okay, the name will be what? Methyl for this substituent. Okay, so if we are naming from this side, okay, as this side as our longest chain, then we have the first methyl on carbon 3, so we have what? 3 methyl. Okay, then our second methyl will be on 4, so we have 4 methyl. Okay, so overall we have what? 7 what? 7 as our number, that is the positions of the methyl groups. Okay, now if we are counting in the reverse way, which is this side, okay, then our first methyl will be on carbon 2, so we have 2 methyl. Then our second methyl will be on carbon 3, so we have 3 methyl. Okay, now if we add the numbers, we have 5. Okay, so in naming organic compounds, you want to take the one with the least locant. Okay, so in this case we will prefer to have the compound named with the least locant than a higher locant. Okay, so in this example, the naming from this side where we have the yellow marking as our longest continuous chain will not be favorable, because what? It will give the substituent a higher locant, and we don't want that. So in this example, we'll be naming the carbons from the right side, so we name from the right to the left, okay, so that we can get our least locant. So I'll be taking this off. Okay, then I'll be moving these two up. Okay, so now that we have that down, let's now name our compound. So we know we have 2 substituents, and then our parent name is pentane, sorry. So these two, we have methyl methyl, okay, so it will be dimethyl. So we have what? 2,3 dimethyl. Okay, so we just join this substituent with the parent name, and then we have the name of our compound. So the name of this compound, okay, is going to be what? 2,3 dimethyl pentane as the name of this compound. Now let's name one more example, and then we look at how to draw the structure of a compound when you are given the name. So let's have a very long one. So this one we have this, then we have CH, then attached to that we have CH3, and we have carbon again with 2 H's, then we have another carbon with an H, then with C2H5, then we have C with Br, which is a bromine, then we have hydrogen, then we have this, we have CH, we have C with an H, and then below here we have CH3, and then we have another CH3 over here. Okay, so let me write this side wall. So this one will also be like this. Okay, so as usual, we name the longest continuous chain, and the longest one we can see so far is this one. Mind you, the longest continuous chain can be branched. Okay, so it can be, this is 2 carbons, so 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7. In this example we have 7, so we will not consider the branch one. Okay, in some examples the longest continuous chain can branch, like it can branch, it go like this, comes like this, and like that. Okay, it can be branched, so it's not always straight. So now let's name the carbon. So let's name from the left to the right. So we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, and then carbon 7. Then we also name from the right to the left. So we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7. So at this point in time we don't know which position, like where we are counting from, we don't know the ones that will favor our substituent, we don't know it. but all we know is that we have 7 carbons, and then for 7 carbons the name is what? Heptane. So our parent name over here is what? Heptane. Now that we know this is heptane, we can find out that we have this group, okay, this group, and then this group not being part of the parent structure, and they are also not hydrogen, so they are what? Substituents. Okay, so because they are substituents, let's now try to name them. So we can see we have, if we are taking the yellow as the counting, so we have one group on carbon 2, so we have, this is a methyl group as I showed earlier, so it's 2 methyl. Okay, then we have 4, this is 2 carbons and then 5 hydrogen, so this is ethyl. Okay, it's also an alkyl substituent, but then it's lacking 1 hydrogen. Okay, so it's an ethyl. Okay, so this will be what? This will be 4 ethyl. Okay, then we have 5 bromo, we have bromine on 5. Okay, so 5 bromo. Then we have a CH3 on carbon 6. Okay, so we have 6 methyl again. If we add the numbers, we have this and this will give us 10, this and this is 17, so we have 17. So now let's look at the numbering from the left to the right. So from the left to the right, we have 1 on carbon 2, so we have 2 methyl again. Okay, then we have 3 bromo, bromine will be on 3 bromo. Then the ethyl will be on 4, so 4 ethyl. Okay, then the last methyl will be on 6, so we have 6 what? Methyl. Okay, so if we add the numbers, this is 10, this is 15, so we have 15. So in this example, okay, the yellow ones will not be correct because what? They will give us 17, which is a higher locant. Okay, so we prefer to go with the one with the lowest locant, which is 15. So in this example, we are nullifying the red part. Okay, so these are our substituents. Now that we have identified all our substituents, let's now group them together. Now in naming the substituent, I said earlier on, we arrange them alphabetically. So let's see how we are going to write all these substituents. So alphabetically, we have M, B, and E. Okay, then the methyl is still a repetition, so B comes before E, so we have what? 3 bromo. Okay, then the one that come after B in this one will be E, so we have what? 4 ethyl. Okay, 3 bromo, 4 ethyl. Then we have methyl group, which is M, which will be the last in this one, so we have 1 on carbon 2, 1 on carbon 6. Okay, so we need to specify their position, their location. So we have what? 2,6 dimethyl. Okay, so it will not be 2 methyl 6 methyl, no, it will be what? 2,6 dimethyl. Okay, now that we have our substituents arranged, all we have to do is what? Add the parent name, so which is what? Heptane, and then this is the name of our compound. So in this particular example, the name of this compound is what? 3 bromo, 4 ethyl, 2,6 dimethyl heptane. This is the name of our compound. Yeah, as simple as ABC. But then if you are new here, you have to keep practicing to know how to name this, and that is what this tutorial is here to do. Okay, for those of you who want to copy, quickly copy, and then let me take it off. So I'm sure by now you've copied, so I can take it off. Okay, all right. So there is also this possibility of you, let's say in an exam, they will give you the name of the compound and then they will ask you to draw the structure. So let's have a look at one example and then we end this tutorial. So we have 2266 tetramethyl heptane as our example. So we have to draw the structure of this compound using the name. Now first thing you have to do when you have such a question is look at the parent name. So in this example, the parent name is heptane, and we know heptane, it means what? Carbon 7. So it means we have 7 carbons. So you just write what? 7 carbons. 1, 2, 3, 4, 5, 6, and 7. So we now have our parent structure laid down to rest. Now we can see we have here what? This is example 1. So we have 2266 what? Tetramethyl. So it means what? We have 4 methyl groups, okay, on different positions on this parent structure. 4 methyl groups, and then methyl is what? CH3. Okay, so all we have to do is, if this case, it doesn't matter where you are counting from, okay, whether you are counting from here or from here, you will get to decide. So if I'm going from here, I can decide to put the first methyl, okay, since they are both on carbon 2, this is carbon 1, carbon 2, so I'll put CH3 here, and then another CH3 here, and then that is okay. Then the next one is saying 6 6, okay, so I'll put the other one on. This is carbon 2, this is carbon 3, carbon 4, carbon 5, carbon 6, so CH3 and then CH3. Okay, so now that I have all my substituents laid down, all I have to do is what? Add hydrogens. Okay, so we know carbon forms 4 bonds, so 1 2 3 4, so this is complete, this is also complete. This one has 2, so we have 1 1 here. This one 1 2, so 3 4. This one also 1 2 3 4. This one has 4, this one has only 1, so 1 2 3. So we just add hydrogens over here to all the other sides, and then bam, we have the structure of the compound. So in this example, this is the structure of 2266 tetramethyl heptane. Let's have a look at one final example, and then we call it a tutorial. Okay, okay, so the second example we have over here is what? 5 bromo 2,6 dimethyl octane. Now as usual, we look at the parent name, which is what? Octane. So octanes mean what? We have 8 carbons, so we write 1 2 3 4 5 6 7 8. Okay, then try to add all the strokes to it. So here, 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 and then here, here, and here. Okay, so now we can see we have 3 substituents. Okay, we have 1 bromine, then 2 methyl groups. Okay, so the bromine is said to be on carbon 5. So if this is our carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7, 8, then our bromine is on carbon 5. You can either put it here or put it here, it doesn't really matter. So Br over here. Then we have 2,6 dimethyl. So we have a methyl group, this group. Okay, one is on position number 2, one is on position number 6. Okay, so it means this is carbon 2, so we can write the methyl over the CH3 at the top over here, and then carbon 6, this is carbon 6, we can write another CH3 over here. Okay, so now that we've exhausted all the substituents, all we have left is to add what? Hydrogens. Hydrogens all around. Okay, so these are all hydrogens. Okay, so yeah, so this is how you get to draw the structure of an organic compound or an alkane using the name. I hope you guys enjoyed this video and you've learned something. Okay, so I'll see you in the next video. Bye bye. Hello and welcome to my science tutorials. In today's video we are going to be looking at reactions of alkanes. So without wasting my time, let's get started. Now alkanes are generally unreactive, okay, so they normally tend to undergo a reaction we call substitution reaction. So what causes this unreactivity on the part of alkanes? Now alkanes, let me give the simplest example, which is a methane. Okay, the bond between the carbon and then the hydrogen that we are seeing over here, okay, was as a result of an easier or head overlap between what the orbitals of the carbon and then the orbitals of hydrogen. Now we know easier or head-on overlap. This overlaps leads to a very strong, okay, a very strong bond. Okay, so as a result, the carbon hydrogen bonds over here are very strong, that before we break them we need a very high energy to break this bond. Okay, so because the single covalent bond formed in alkanes are so strong, they require very high amount of energy to break them. Okay, so because this energy is so high that normally it is not attained during reaction mechanisms, these bonds cannot be broken. Okay, so the only thing that can be done over here is for what, one of the hydrogens or more of the hydrogens to be substituted, and then when this substitution occurs, we then tend to call the reaction that occurs, okay, substitution reaction. So for example, maybe we have let's say a compound B here. Okay, so in the process we will have compound B replacing the hydrogen over here, so we'll be having this, okay, this is 3 attached to compound B, and then we will be having HB as our byproduct. Okay, so this is a typical example of what, a substitution reaction, a reaction we are calling substitution reaction. Now this is the reaction that alkanes undergo, and then so what is the substitution reaction in the first place? So this is a reaction in which an atom or group of atoms, okay, is replaced by another atom or groups of atom. Okay, so we have an atom over here. When we replace it with another atom, then it becomes what, substitution, because we could see at the end the bond over here is not broken, only the atom at the edge over here is being replaced by another atom. So this reaction can be called substitution reaction. Now alkanes undergo halogenations. Okay, they undergo halogenation, that is, we can add the halogens to them, that is, we can add chlorine, bromine, and even iodine to them. Okay, so they normally tends to undergo halogenation. Okay, so in this tutorial video we are going to look at how the halogenations of alkanes actually occur in the presence of UV light. Okay, so now halogenation of alkanes undergo substitution reaction with halogens, okay, to yield haloalkanes and hydrogen chloride. Okay, so what we mean by haloalkane is just an alkane group, let's say CH3, okay, attached to a halogen. Okay, so this is a haloalkane. Okay, so this a typical example of a haloalkane, and then plus what, HCl or what, HBr, depends on the type of halogen we use in the reaction. Then we will either be getting HCl or HBr as the byproduct. Now this reaction, okay, it occurs in the presence of what, sunlight. Okay, we need sunlight or UV light, okay, for this reaction to occur. So assuming you want to carry out a halogenation of an alkane, and then you place your reaction vessels, okay, or in the dark, you place it in the dark, the reaction will not occur, because the initial stage of the reaction requires the presence of sunlight to be able to be carried out. Okay, so without the presence of sunlight or UV, the reaction will not occur. So before we look deeper into the reaction mechanism that goes into the halogenation of alkanes, let's have a look at the various types of bond cleavages that occur, or bond breakages. Now there are 2 types of bond breakages. Okay, so we have one, the homolytic cleavage. We have the homolytic, and then 2, we have the heterolytic. Now the homolytic cleavage, okay, the first one over here, this is the bond breaking where an electron from the bonding pair in the bond is equally distributed among the atoms. Okay, so what we mean by this, okay, is that in homolytic cleavage, let's say we have atom A attached to atom B. Okay, the electron pair we have over here, the bond that we formed over here has what? An electron pair, that is 2 electrons. Okay, so in homolytic cleavage, when this bond is going to break, the electron over here, one of them will be given onto this atom, and then the second one will be given to this atom. So at the end, we'll be forming what? Radicals, free radicals. Okay, so this is a typical example of what? A homolytic cleavage. This is an example of how, or this is how a homolytic cleavage occurs. Okay, now mind you, do you see how I use the arrows? I use a half arrow. Okay, this is to show that the transfer of electron is not complete, it's partial. Okay, so it means the electrons in the bond over here are being shared equally between the atoms that are connected together. Now in heterolytic cleavage, okay, the second one, the opposite of this happens, in the sense that the atom that is most electronegative tends to have all the shared pair of electrons being put onto it. Okay, so assuming we have, let me use the same example, A and B, and then let's say B is more electronegative, sorry. So it means the shared pair of electrons over here, both of them will be moved onto B. Okay, so in this case we will be forming what? Cation. We will be forming A plus, and then we'll be forming what? B minus. Now in this case, the A is now what? When it is an organic compound, okay, and this occurs, we call it a carbocation. Okay, let me use a well-defined example. So assuming we have methane, okay, so we have CH3 attached to H, this methane, okay, undergoing a heterolytic cleavage. It means all the let me use methyl bromide. Okay, this is a perfect example. So in this case, the shared pair of electrons is being put onto the bromine. Okay, so at the end we'll be getting what? A methyl cation plus bromine anion. Okay, so in this example, the methyl cation over here is what we call as what? A carbocation. Okay, this is a carbocation, that is a carbon bearing a positive charge, so it's a cation, and then it's carbon is the one bearing the charge, so it's carbocation. Okay, so these two forms of cleavages are really important when we are dealing with what? Halogenations of alkanes. So now that we know the types of bond cleavages that occur, and then what are formed at the end of each cleavage, let's go. Okay, in homolytic we form what? Free radicals. Okay, free radicals. And then in heterolytic cleavage you form carbocation. Now the free radicals that have been formed over here, they are really reactive. Okay, so because they have an electron over here, and then electron is needed for reactions to occur, so they are really reactive. Once it starts, then they continue, they just go like that. It's really amazing. So let's have a look at the mechanism of halogenations of alkanes, and then you get to appreciate what I'm talking about. So we are going to look at what? Halogenation of what? Of alkanes. All right, so the general reaction that we normally write is, assuming we have methane, which is the simplest alkane ever, plus chlorine molecule. Okay, this will give us what? CH3Cl, okay, methyl chloride plus HCl. Okay, so this is an example of what? A substitution reaction, specifically halogenation or chlorination. Okay, so this is what? Chlorination. This is chlorination of alkane. Okay, now this chlorination, okay, this is just the overview. This is just how the reaction proceeds, but how the chlorine tends to attack the methane, okay, to now have a methyl chloride, and then HCl occurs in 4 steps. Okay, so let's have a look at these steps. Okay, so the first step, which is step 1, is what we normally call the initiation stage, or the initiation step. Okay, now this is the step that requires the use of the sunlight or UV for it to occur. That is the more reason why if you carry out this experiment in the dark, it will not occur, because the radicals that are needed to start the reaction occurs in the presence of sunlight. Okay, so if you put them in the dark, they will not be produced, and then the reaction cannot proceed, will not even start in the first place. So let's have a look at what happens. So in the initiation step, okay, we have the chlorine molecule, okay, Cl attached to another Cl, okay, in the presence of what? Sunlight, okay, sunlight or UV, okay, you can just write sunlight or UV, undergoing what? A homolytic cleavage, okay. So it means an electron will be given here, one electron, and then another one will be given to this chlorine molecule over here. So we'll be forming what? Chlorine radicals. We'll be forming chlorine radicals in the first stage, which is what? The initiation step of this reaction. Now step 2, okay, now step 2 and step 3 are called what? The propagation step, okay. So propagation step, okay. Now in the propagation step, what happens? One of the radicals over here, the free radicals, now attacks the methane that we have over here, okay, to now form something. So we have the methane CH3 attached to an H, okay, plus the radical. Then what happens? Okay, now the radical over here picks up the hydrogen over here and then gives the electron to the alkyl functional group that is being put, which is the methyl, okay. So at the end we'll be getting what? We have CH3, then the radical, this electron over here is being given to the CH3, then plus the HCl, okay. So the chlorine will pick the hydrogen over here, so we have HCl, okay. So this is the second step, is the step in the reaction mechanism where the HCl is produced, what we have over here as the byproduct, okay. So that is where the HCl is being produced. Now once we have the CH3, which is the methyl radical in solution, then we go to step 3, which is also what? The propagation step, okay. Then this, now the methyl radical CH3 dot, okay, now attacks a new molecule of what? Chlorine. Now we know this doesn't mean we have just one chlorine molecule in the solution, okay. So just one mole of what? Chlorine contains what? The Avogadro's number of what? Atoms, okay. So it means when we have looking at the Avogadro's number, is quite a huge number, okay. So which means when we use 1 mole of chlorine, it means we have the Avogadro number of what? Chlorine molecules, which is very much, like, it's plenty, okay. So the methyl radical over here now attacks the chlorine molecule, okay, another chlorine molecule in the solution to form what? CH3 Cl, okay. Over here the chlorine, the methyl radical attacks the chlorine, okay, picks one chlorine and then give the electron to the second chlorine in the solution, okay. So we now have what? Chlorine radical being produced again, okay. So up to over here, okay, this is where we get what? Our product, which is what? The alkyl chloride, okay, or the haloalkane, okay. So this is in the second step, we get the byproduct, which is the HCl, and then in the third step we get our product, which is the main product that we are after, haloalkane. But then what happens? Let's take a look at this. Because we still have chlorine molecule, okay, chlorine radical, sorry, we still have chlorine radical inside the solution. It means this mechanism, okay, or this reaction can continue further, okay. So let me read something very, very important for you. Now if the methane molecule is not in excess, which means what? If we have what? The methane molecule as what? As the limiting reagent. If we have the methane as the limiting reagent, which means it is not plenty or it is not many, okay. If we have the methane molecule not in excess, okay, it means what? Step 2 and step 3 can be repeated to give us what? Di, tri, and what? Tetrachloromethane, okay. So it means if we have this, okay, in limited amount, okay, if we have this, the CH4 in limited amount, something interesting happens, okay. So after we form the CH3, Cl, it then now reacts with the chlorine radical formed again. So normally this is where the reaction stops. Okay, we get our product and then we get the chlorine radical. Okay, but then if the question tells you you have the methane molecule, okay, as the limiting reagent, or it's not in SS, it means what? The chlorine radical again, because of its being a radical and it is very reactive, like I said, will then attack the haloalkane again to form another product. So it will attack again, then pick one hydrogen and then give the electron over here to the haloalkane. So we'll be forming what? CH2 Cl radical plus HCl. Okay, then from there let's call this step 4. Then from there, then step 5. Okay, then step 5, we have the CH2 Cl radical will now attack a new molecule of what? Chlorine. Okay, to give us what? CH2 Cl, which is dichloro what? Methane plus Cl radical again. Okay, so you could see at the first part we over here we have what? Chloromethane. But then if the methane is in limiting reagent, okay, or it's not many, it's not in excess, okay, the reaction will continue to step 4, where we will have what? We will form the CH2 Cl radical again, and then if that occurs, okay, this now becomes a radical which is very reactive, and then it will now go and then attacks a new chlorine molecule to form what? Dichloromethane. And then this further continues because we still have chlorine radical inside the solution. Okay, so this will continue until we get what? Trichloromethane, and then at last we get what? Tetrachloromethane. Okay, so this reaction is said to be what? A chain reaction. A chain reaction in the sense that once the reaction starts, okay, it continues on its own. Okay, so after the radicals are formed over here, after the radicals are formed, if you now put the reaction, let's say in the dark, the reaction will continue because the chlorine radicals are already produced. So the first step is the only step in the reaction that needs the sunlight. Okay, sorry for all the background noises. So the first step in the reaction is the only step that needs the sunlight. After that, the other steps, okay, do not need the sunlight. In the absence of the sunlight, they can still continue to produce our product, which is a haloalkane. Now on the other hand, if the methane is in excess, then the chlorine free radicals, okay, attack a fresh methane molecule as shown in step 2 and step 3, okay, to give us what? A repeated chloromethane. Okay, so assuming we have CH4 in excess, okay, if we have CH4 in excess, it means after we are done over here, okay, this chlorine radical will not attack this product anymore. It will not go and attack the new methane molecule in solution to give us what? Another chloromethane. So we have what? Chloromethane produced in excess. Okay, but in the absence of what? Excess methane, they will be forming what? Dichloromethane, trichloromethane, and then tetrachloromethane. So this is how halogenation of alkanes occur in the presence of sunlight. So I hope you've learned something, and this video actually helps you know how to go about with your halogenation of alkanes. Okay, so this video is just a quick overview of the halogenation of alkanes. So I hope you learned something. So thank you so much for watching, and then I'll see you in the next video. Bye bye.